right? So here is the set of reals that are greater or equal to 0, right? I gave it some name. It's a reasonable name, right? And what is a minimum value, right? We need a definition of a minimum value, right? 0 is a minimum value because every other object that is in the set is bigger, right? Everybody buy that, right? 0, in fact, 0 is in the set, and it's the minimum because every other number in the set is bigger. Everybody buy that? Right? Right? And why does the set have a minimum? Because there exists a number that's in the set that's a minimum. Why is it the minimum? Because every other value in the set is bigger. Everybody get that this is the definition of minimum, right? Any debate about it? All right. Here's another set. It's the same set except I removed 0. All right? So this is the set of all reals that are strictly bigger than 0, right? And the question I want everybody to think about is, what is the minimum value in this set? All right? Anybody have an idea? Here's one vote. How many people think it doesn't have a minimum? Any other ideas? If you think it does have a minimum, what would it be? 1. Well, the problem is we're doing reals, right? So a half is a real. 1's not the, right? That's a good guess. Does have a minimum value. 0 can't be the minimum because it's not in the set, right? 1 can't be the minimum because a half is in the set and is smaller, right? And this number here can't be the minimum because this number is smaller, right? You could say, well, the minimum is like this, but has an infinite description that has lots and lots of zeros, right? But you haven't really told me what number you're talking about. You're telling me some number is the minimum. I need to know what that number is, right? Everybody get that? So maybe it doesn't have a minimum. Oh, here's our little picture. Right? Is everybody? Oh, would you go away? You know I don't like you. Go away. All right, so it's everybody in the orange, right? The little circle means we're not including 0. You probably did that in high school, right? All right, so if it's not, how would we prove that it doesn't have a minimum, right? This statement up here is the statement that it has a minimum. Remember, there exists a number in the set that's the minimum. And why is it the minimum? Because for every other guy in the set is bigger, right? So we negate that. We turn the exists into a Forall and the Forall into exists. And remember, like our dogs, we don't change the fact we're talking about things in our set, right? And then we say, well, in the end, X is bigger, right? So what is this saying? It's saying, you give me any number, I can give you another number that's in the set that's smaller, right? Right, so every X fails to be the minimum because there's smaller values in the set, right? Does that make sense? So let's play the game. It says for all guys in the set. So how do we start? Come on, guys. Come on. Everybody move. Can you move? Are you alive? Good. Let X be an arbitrary value, right? And more than that. We need it to be an arbitrary value in the set, right? So here's an arbitrary real value bigger than 0, right? Now, what do I have to do next? I have to come up with a y. What should my y be? Half of it, right? Here, proof by picture, right? There's my x, there's my y, which is half of it, right? And then I think about it. I said, well, it's in the set because it's still bigger than 0, right? And it's smaller than x. So we're done. Everybody good with that? So it's kind of fun to see there's no minimum. All right. All right. Opposed to integers, right? He was saying, what about 1 being the minimum, right? One thing we could, I don't know if we can prove this, but it's sort of, it might, because it might be an axiom about integers, is that if you have any set of integers that's either finite or at least has a bound from below, right? Here, right, this is a set of reals that is bounded from below by something. But if this was a set of integers bounded by below, then it would have a minimum value, right? So that's a fundamental difference between reals and integers, right? Right? Oh, here's just, have you guys heard of supremums? All right. So, so 0 in this set, you must admit, is still special, right? It's not a minimum, but it's somehow special, right? Right, because -3 is also smaller. I mean, 0 is smaller than everybody in the set, right? But -3 is also smaller than everybody in the set. But why is 0 better than -3? Is the biggest. Exactly, right? So 0 is the biggest value that is less than everybody in the set, right? And, right, so here, I knew the word supremum, but I must admit I couldn't remember what the opposite was and had to Google it. So it's called an infima. I don't remember that. It's the biggest value of x such that everybody in the set is it's the biggest value of x such that it's smaller than everybody in the set, right? So if you're reading math papers, it often talks about supremums. And why does it do supremums? It's like a maximum, except the value is not in your set. All right, everybody good? All right, so now we're going to do something harder. And the reason we're going to do it is because when we were teaching 1019 last term, lots of the students were taking calculus. And in that class, unlike you guys, they actually talked to me. And they came to office hours. And when they came to office hours, sometimes they didn't want to talk about this material. They wanted to talk about calculus. Why? Because they were being forced to prove things in calculus, and they had no idea how to do it. And the professor wasn't teaching them what a proof was. All right? And so we covered some of it. All right? So this idea of an epsilon delta proof is fundamental to calculus. Right? So it's all about Forall exists, right? And so let's do this example, right? Right. So how does epsilon deltas work, right? Both epsilon and delta are little values, right? In fact, calculus was simultaneously, I don't know if you know this, proved by 2 people, Newton and Leibniz. Story about Newton is he was about your age, I think. He was supposed to be going to college, but there was a pandemic, and he was forced to go home, and he couldn't do Zoom. So what did he do at home? He invented all of physics and calculus. All right? He wasn't on his phone. So I forget whether he did the limits or whether he did the infinitesimals. One of them, Leibniz, did infinitesimals, right? But here, x and y, so you could think epsilon and delta are infinitesimals, which are really small values bigger than 0. But we're going to say that there are always actual real numbers, but small, right? And what are we saying? The adversary can give us, right? It's a Forall epsilon. So the adversary can give us any little epsilon that he wants. And it's going to be small, small, small. He can give it as small as he wants. And we're okay with that. He can give us his worst case epsilon as long as after he tells us the epsilon, we get to come up with delta, right? And the reason we're going to win the game, remember the game we were playing where he came up with a number and I came up with a bigger number, right? I win because I went first. I went second, right? We're going to win because we get to choose our delta second, right? Everybody get that? All right. So there are many things we could prove in calculus. And one thing what we're gonna do now is define what it means for a function to be continuous. All right. So you look at that function, it looks continuous to you, right? It doesn't. What does it mean? It doesn't suddenly change value. It doesn't go from 0 to 1 instantly, right? So now, where is it continuous? Well, we want it to be continuous everywhere, right? So we're going to say for all values of x, our function f is continuous at this value of x, right? Does that make sense? It's not going to suddenly jump at this x. All right, and so then, now, our adversary, of course, is trying to fight us. Our adversary wants to argue that it's not continuous. And his first complaint will be, well, f seems to be changing. You're claiming, it doesn't change fast, but it is changing, right? So we come back and say, yeah, it changes, right here. Oh, here's the adversary still complaining. It says, look it changed, right? And we can say, yeah, but if it never changed, it would be a constant. The function would be constant, and it's not constant, right? It does change, right? So we need to allow some change, and I'm also going to complain about what the adversary did was he got a change, but he changed the x by an awfully lot, right? In order to get a big change, he had to get a big change in f. He got a big change in x. Right? So that's no good. All right, so let's quantify it. If we say we're only allowed a small change, right? Well, how small of a change are we allowed? Right? Are we allowed for it to change by 0.1, by 0.001? Right? How much of a change are we allowed? And right, we want to be the adversary to get to choose how small of a change we're going to allow. All right. So the adversary says, yeah, I'll let you change, but I'm not going to let you change by, he's going to provide an epsilon, right? It's bigger than 0, but it's really small, right? And he's going to say, I'm not going to let you choose to change more than by this really small bit. And if the meaner he is, the smaller he makes epsilon, right? Does that make sense? All right. Right. So I say, sure, cool. I can honor that, right? But I get to choose my delta, right? And my delta says, yeah, I can assure you f doesn't change by more than epsilon as long as you don't change x. Oh no, f doesn't change by more than epsilon as long as you don't change x by more than delta, right? So the oracle says, okay, I'm going to change x, but I'm going to honor that I can't change it more than delta, right? So here's the game, right? We're saying adversary says which x is we're going to see if it's continuous. The adversary gets to say the definition of a small change. The prover gets to say how much you can change x by. And then the adversary says, all right, I will change x, but I won't change it by more than you're saying, right? Right, so here, I think I got an animation here, right? Here, see that? The x can change by anything than that, then f doesn't change by more than that, right? Does that make sense? And so that we're saying, if you change the x within this little interval, then f won't change by more than that, right? Everybody get the definition? Right? And if you're doing calculus, these epsilon delta proofs come up all the time, right? All right, so here let's do a concrete example. F is x squared. Oh, do I not plot x squared, right? So here's our definition that we want to prove. And you might say, uh-oh, right? This is an example where you go to your calculus teacher says, I want you to prove that x squared is continuous. And you say, well, okay, great. Well, give me the definition of continuous. And they have to give you a definition, right? And they could make it English hairy-fairy, and you're not really sure what they're saying, right? But you get between you and your calculus teacher, you write down a concrete definition, right? And now, in order to prove it, you just have to play the game, all right? So, right, so you say, hey, what is x? Let x be arbitrary. I don't know, I'm making it arbitrary, but I'm making it bigger than 0. It could be less than 0, but the proof would be similar, but we would have to deal with the absolute value signs would be harder, right? All right, so x is something. Then he comes up with an arbitrary epsilon, really, really small. And then I have to come up with the delta, right? And you look at my definition of delta, you might say, dude, 1, how'd you come up with that? And 2, it's a pretty weird delta because look at, there's a delta on both sides of the equation, right? Is that really a definition? Well, we could, in some ways, you can think x is a big number, right? It was given first. Well, epsilon is a small number, right? So here, this epsilon is making delta a small number. And if delta is a small number, adding it onto x isn't going to make a big difference, right? So we could work out, given an epsilon, we could work out what my delta is, right? But I'm going to just do this because why? Because I looked ahead and I figured it was what we needed, right? So now we continue on. The adversary gives me an arbitrary x that's in this range. And again, it could be either side, but just to make our life more concrete, let's say that it's on the bigger side, right? So it's between those, right? There's our x, and then we just plug it in and crank. And if you plug it in, right, we plug it in. Here's the new value of x, right? Here's right. If the new value of x was smaller than it, it's in this range. But the worst case is when it's as big as possible, right? So we make it as big as possible, and then you multiply it out, and it just works, right? And why did it work? It's because I set delta to be the right thing, right? Everybody follow that? Any questions about this? How many of you have done this kind of thing in calculus class? And how many of you were lost at the time? How many would have preferred if we had talked about this game? Right? Does this help a little bit? Right? All right. All right, so here's another function, right? And is this one continuous? No, right? It's this 3 up until this value. At this value, it's 3, and then it leaps up, right? But it's almost continuous, right? It doesn't change by very much, right? But is it continuous? No, it's not. So we negate it, right? We switch all the Foralls to exists and back and forth, right? And we flip this sign here. Everybody see what we're doing? And then we play the game, right? I have to come up with a value of x. Well, what's the meaning of x? X is where I'm claiming it's not continuous, right? So where is it not continuous? It's not continuous at 5, right? So I make x 5, right? Everybody good? And then we say, what's next? Well, I have to come up with an epsilon. Well, it's changing by 0.002, and so I'm only, how much change am I going to allow? I can make the allowed change as small as I want. So I make the allowed change smaller than the change that there is, right? Because I want to prove that the change is too much, right? I'm going to say that 0.002 is too much. Why? Because the allowed change is right? And then then it's a Forall delta, right? So we're making delta arbitrarily small, right? I just gave an example here to say, what would be a bad delta for us. And then we plug it in and see, right? Oh, then, right? And he's coming up, he comes up with, we're proving this one down here. So he came up with the epsilon, the delta, and then we get to come up with an x in that range, right? So we set our x to be the furthest in his range, and we check, and you plug in the math and the gap, right? No matter how, the point is, no matter how close you are in this end, there's going to be a gap between 3 and, right? Everybody follow this?